One again. Welcome to the part 2 of geometric aspects of the Swampland. As you know, this is an initiative in which we try to involve both geometers and theoretical physics to try to get something out of this subject that has common interest for both. And just like in part 1, the first lecture of part 2 is going to involve some introduction, which will be given by Thomas Grimm from Utrecht University. And he will focus more, I believe, on all these topics that we are going to discuss in part 2 that are more specific. And I believe that there's no one better than Thomas to do this introduction, because he has been leading this field in which he extracted some algebraic geometric results to learn a lot about the Swampland program and some of his conjectures. It all started with some applications of the Finiteness Conjecture, but this has evolved. The applications are much broader, and which is a symptom that these Swampland conjectures are all interconnected among each other. So without further ado, I'll let Thomas start, and please, Thomas, give us your overview of the subject. Thank you.
Okay, well, thanks a lot. Well, first of all, many thanks to the organizers for putting this together. I know it was not easy, and it's very nice that we can finally meet in person and that you really make the effort to bring everyone together, even though it has its challenges. In any case, I'm very happy to speak here, and Fernando already gave some introductory words. And this is also indeed exactly the spirit of my lecture. Namely, what I want to do is I want to introduce you to the subject such that the mathematicians are maybe getting a little bit of a glimpse of our way of approaching this, and the physicists see first pieces of mathematics entering the discussion. It will not be extremely, I will not be able to go extremely far, but I hope nevertheless that you all get some piece out of this introductory part. So let me start. Now I have to remember where I have to stand. So I want to start with comments on the Swampland program. So I think you have seen this before. So the basic approach or the basic question is the following. So we as physicists, we know for a long time that there are a large set of quantum field theories. So there are many quantum field theories which we know. It's a huge set that can be constructed. And they all, if you take the basic consistency conditions into account, they all look equally fine. Now, as people working on string theory, what we realize is that if we do string theory and we try to connect it with these huge set of quantum field theories, so if you're a mathematician, you maybe don't know what that is, but just imagine that it's a large set of models, yeah, in whatever, you can make a very precise notion of what a model is, and a large set of models, but some of these models, they come easily out of string theory, and some other models, they just seem to not come at all out of string theory. So what we actually find is that only a subset of this gigantic set of quantum field theories come out of string theory. Yeah. And what the Swampland program does, it tries to give principles that select those which are compatible with string theory. Now, we are courageous people, and people in the Swampland program are very courageous. So they sometimes are a little bit more bold on this. They just say, well, string theory is a theory of quantum gravity. So instead of writing here, selecting those which come out of string theory, you could also say those which come out of quantum gravity. Of course, we don't know, we might not know all the theories of quantum gravity you can envision. Maybe string theory is the only one, and so on. So one should take these sort of generalizations with a grain of salt. So I will use for string theory the abbreviation ST, and for quantum gravity I will use the abbreviation QG. So this is the basic idea, to select these models which are also coming out of string theory. So it's very, in itself, it's a very simple idea. And the idea is simple, but doing this in practice is very, very complicated, right? Because we don't understand, as I mentioned, quantum gravity in all its aspects, and we even don't understand string theory in all its aspects. Yeah. So therefore, we do something very scientific. We don't say that we have found these principles, but we formulate these principles as conjectures. So this led to several bold conjectures. And these conjectures are based on known examples. And for some of these conjectures, there are independently some black hole arguments. Yeah. But to be fair, in many cases, the best evidence actually comes from known examples within string theory. Yeah. Now, for those of you who are more on the mathematical side, this is something very familiar in mathematics, this approach. Yeah. So in mathematics, there are many famous conjectures, and we will touch in these lectures maybe on some of them. For example, the Hodge conjecture you have certainly heard about. Yeah. And for the Hodge conjecture, you can make similar arguments. Of course, in mathematics, it's different, right? You can prove things directly. But also for these mathematics conjectures, you can make similar arguments as they appear here. Namely, they are just built from intuition from some of the experts in the field. Yeah, the evidence can be actually very sparse. Yeah, for example, it's not the case that for the Hodge conjecture that the evidence is somehow overwhelming. But there's also no counterexample, obviously, and that would be a killer in mathematics. And a very important fact, they might be wrong. Yeah, so it could very well be even that this, when it has been shown in the past that like the original formulation of the Hodge conjecture was simply too strong, it was shown to be wrong, so you have to adjust the conjecture. And all of this applies to the Swampland conjectures. What is different is that in mathematics, we are able to prove things, while in these theories of quantum gravity, it's much harder to prove things because the framework is not as rigid. Yeah, it's not as well understood. So how could we make progress then? And that will be the aim of these lectures, is to do the following. So we want to study these conjectures in reasonably well understood settings, string theory settings, once we look at one of these string theory settings, then we are in business because, as I will sketch briefly, string theory is highly related to geometry. And many of you know this, because then we can translate the conjecture into a mathematics statement. And finally, well, once we are there, we are in the clean world of mathematics, and therefore we can prove the statement or disprove it, of course. Let me add that one of the big discussion points, if you follow one of these Swampland workshops, is that even the part one is not necessarily agreed upon by all the people working on the field. So this is a tricky part to address. So what is a reasonably well understood setting where we can test these conjectures? Yeah, so we have to overcome this point. But once we are in part two and we translated this into a math statement, it can be either right or wrong. Yeah. And you can just work in this part independently of whether or not you believe this precise statement. And we will see an example of this in my last lecture. I will give somehow a proof, an actual mathematics proof of one of these physics conjectures. Now, let me now, after this general words, I should look at the time. Where can I see the time?
Okay, I have a question. So these subsets that come from string theory, should they be thought of as submanifolds of some non-zero codimension or open sets?
You should not think of this too hard. That's probably the best way of saying it. So the problem is, what is this? I draw it as a manifold, which is kind of an illustration. So the best way maybe of thinking about this is as an abstract set. It's just some topology. So, and even this it's tricky to make clear, because with what sort of data do you label a theory? And it could be discrete. It could be over the integer numbers. It could be over some real numbers. So it's a very complicated object which I'm drawing here, very schematic. Okay, cool. Yes, so this is the typical thing, so it goes over slow. Okay, now the aim is to give you conjectures and discuss them a bit, and I will not try the impossible and introduce all the Swampland conjectures. I don't even know all the Swampland conjectures because there are quite a few at this point. But I will introduce like 2 or 3 which are the most relevant to my lecture series, and they also connect naturally to Hodge theory and to the O-minimal structures and also to the third lecture. So, and one of them which kind of got me interested in the subject is the so-called distance conjecture. And now you have to bear with me for a moment. I will formulate them in a physics way. So it's by Oguri and Waffa, and it's from 2006. So for mathematicians, that's rather recent. For physicists, it's rather long ago. So what is the statement? We consider an effective theory with scalars phi I, with kinetic terms like this. And no scalar potential. So what is this statement saying? Well, essentially, it's setting up the properties of one of these quantum field theories, which I want to discuss. So you have to imagine that this specifies a property of the model which I'm discussing. Yeah. And then the conjecture says the following: consistency with string theory / quantum gravity now requires the following. If I go with phi I, a distance d, which can become infinite, so a very long distance approaching infinity. This will become clearer in a moment. And what do I mean by distance? Well, distance, there is an object here which actually we want to interpret mathematically as a metric on a manifold. And the distance is actually computed in this metric. Computed in Gij. And then the statement is then an infinite power of states with masses mi reference falls off exponentially. Okay, so what you have to imagine is you have a manifold, a space with a metric, right? There's a manifold M with a metric, which I call G. So G is a metric. M is a manifold. The phi I here are actually local coordinates. So phi I are local coordinates on a manifold M, and G is the metric, which I wrote already down here. Then the statement is that if I move in a region where this metric degenerates, so where the distance becomes really long, even infinitely long, then an infinite tower of states with masses become light. And with light, I mean that, well, they are becoming exponentially light. It's just an exponential suppression in the limit d goes to infinity. So it's a harmlessly looking conjecture. Of course, there's a lot of physics language in there, but especially what we mean by states. But it's concrete enough to have some mathematical formulation. So I already mentioned
Can
that.
you see what is this superscript? Is mi ref? Some
reference mass. Yeah. So just fix some mass there.
So
Okay.
do you always assume that the space-time is non-compact? Right? So
I will come to this indeed. Yes. So what does that mean? So I already mentioned that we have a manifold. We have, say, 2 points in this manifold, P and P0. So just imagine point P being here, point P0 being here in this manifold. And then there's the distance function now computed between P and P0. And if you move in the into the spike here, which is infinitely long in this metric, assumed to be infinitely long in this metric, then this becomes infinite. Okay. Now it was always so what is then the statement is that this is actually an asymptotic statement. It's an asymptotic statement about masses. Now, for mathematicians, maybe masses are not particularly easy to grasp, but maybe you can think, you get a little bit of an idea about this by thinking about masses as being functions on this manifolds or sections, local sections of some bundle over this manifold M, and they map to the real line. So they actually depend on the point of this manifold. Yeah. And then this is just an asymptotic statement. It's a statement about how the mass at the point P, so this function at the point P, compares to the mass at the point P0, namely it should relate with an with this exponential suppression of the distance. Very concrete statement. Yeah. Of course, it becomes even more concrete, and it's important to specify where these functions come from. Yeah, and that will be our goal in translating this into a mass statement. Now, what is a key example? The key example where was sure, please.
Becoming light means literally that thing.
It's really literally means this. Yeah. So the key example is the following. You look at a disk. Yeah. So now we are in two complex dimensions, and you look at the disk. Well, if I just use the Euclidean metric on the complex plane, then infinite distance is out there. But when I use the Poincaré metric, so the Poincaré metric, which in physics way of writing it, but the mathematicians will know what the Poincaré metric is, takes this form. I write down the line element. This is the Poincaré metric. So if I use this metric, then I should rather look at the punctured disk. And indeed, when you move to the center of the punctured disk, so to the puncture, then this metric blows up. So becomes singular, and this is actually an infinite distance. It's of infinite distance away from any point in the disk. So if you start here with your P0, then if you go closer and closer, the distance becomes larger and larger. And it was already mentioned, in order that such a feature can happen, what I described.
So when you say Poincaré metric, do you mean the same thing as a hyperbolic metric?
Yeah.
But then
the hyperbolic metric of the upper half. Right?
But all the points in the hyperbolic metric are hyperbolic space are equivalent, right? So how from one point, like the punctured point is distinguished?
All the points are equivalent.
No, but this is this from the quotient. So you take the upper half plane,
Right.
take the quotient by the group, and then you look at the ACAS on the product before. So this is the
So
metric seen as around ACAS on the quotient.
Right.
So the cuts would be on the boundary. I mean,
Yeah, the point is that this is this around a point in the boundary
okay.
in the quotient.
So
So it's not the
So one interesting conclusion from this is that in order to have such a feature, M actually has to be non-compact. Yeah, this was already mentioned before. And that's something really interesting because as some of you might know is that many of the theorems in algebraic geometry, they use compactness of manifolds. So if you want to address this question here about the distance conjecture, we actually are forced to work on non-compact spaces. And that will be a very nice connection to the lectures by Ben, where he uses this tame geometry or minimal structures, which are very powerful in extending things which are known in algebraic geometry for the compact spaces to non-compact spaces. If you add these additional assumption of that the function are sufficiently tame.
Can't you just take a compact space and say the conjecture holds trivially?
Yes, this you can do that, but then there's nothing to test. So the fact is such things come out of string theory, so there is something to test. Yeah, so such examples come out of string theory, and you will see that in a moment. Namely, you see that moduli spaces of manifolds are non-compact.
But in this example, this has to be non-compact just because the fact that you can go to infinite distance, right?
Yes.
There's nothing about the mass here. You didn't explain what is the mass.
No. So it follows purely from this from the distance argument.
I think in the initial formulation of Oguri-Baffa, they put into the conjecture that this always exists. So the compact case, it wouldn't be a nice moduli space for a quantum gravity theory.
Right.
So, but I don't know what the status of this.
Well, I think in the last discussions we had with Kumran on this, he somehow retracted, saying that this might be too strong of an assumption. I'm not so sure if it is too strong of an assumption, to be honest, because actually all the examples I know are the ones there's always not compact. So it sounds like a very nice conjecture, even putting this in. Yeah, but I will not test it. So I just said I don't assume that is part of it. Okay. Any other questions on this? So this is the first conjecture which I wanted to sketch, and we will make it more mathematical. Don't worry. Yeah. So we are still in the stage of kind of giving the physics statement. Now, the second conjecture which I want to discuss is something which I call the finiteness conjecture. And this is around for a long time. So even before the time where this was called the Swampland program, and it was sketched, ideas appeared in the work of Douglas, which initiate actually many of these ideas about thinking about the set of theories. And then most recently in the formulation of Hamada, Miguel Montero, Irene Valenzuela, and Kumrun-Bach. So you see, it spans almost 20 years in kind of being in the making in some sense. And now, the statement is the following: the number of effective theories from string theory, quantum gravity. You see, I always kind of use this double notation. I don't know if you like it. Valid below a fixed energy cutoff is finite. Finite. Okay, so it's a finiteness conjecture. It's a finiteness conjecture which is hard to understand for mathematicians because it involves this abstract name of effective theory, which is the same thing which I called here quantum field theory. So it's essentially, so if you want to have an intuitive picture of what this is, which I already explained is a bit tricky, is the statement that the number of blobs which I can draw into this gigantic set, connected blobs, should be finite. That would be the idea of this conjecture. And of course, as physicists, we know what effective theories are, and we know how to characterize them. And then you see that there could be sometimes a moduli space, so there could be a flat direction. And then this I should count as one theory, as one modular space. Okay.
It's about the number of connected components of,
So, right,
of those things, whatever
exactly,
they are.
yes, right. So this would be a finiteness conjecture, and as you probably know, there are many mathematics, there are many interesting finiteness conjectures. In fact, there's a huge research direction on some of these finiteness conjectures, which centers around this direction of all minimal geometry, which we will do. Okay. Now, what I did with this conjecture is, in light of this connection to.
Oh, would you see this is equivalent to saying that there are finitely many infrared fixed points?
You mean finitely many conformal field theory? Yeah, the problem is that this is it's a statement about effective theories where you have fixed energy scale. And if you have like a conformal field theory, I don't think that this statement is even true, because you have to cut them off at some point. So we know that if you don't fix this energy scale, you can generate infinite things, infinite towers of things. But as soon as you fix a scale, the statement is that below this scale, below some sort of upper bound, and we will see this in these mathematical formulations later on, then things have to be finite. So, and this significant extension which I want to mention is, which I call the Attainment Conjecture, which I think is much cleaner in some, well, it's actually much cleaner than this statement, which I made in 2000 last year as well. And this is the statement that all the parameter spaces field spaces and coupling functions of those effective theories are definable in an O-minimal structure. So they are definable using tame geometry. I just want to mention this because this gives somehow a cleaner description of this picture, actually, and then it fits precisely together with the idea that there are only finitely many connected components. So we get an introduction into O-minimal geometry, I think, later today, and then you will understand what the statement means. Yeah. Whether or not this is true, of course, is up to debate, as I explained. Okay, very good. So these are the conjectures which I wanted to sketch, and I will, in my lectures, I will discuss the distance conjecture and this finiteness conjecture, but I want to apply it to a concrete geometric situation. So of course, I don't want to keep discussing these conjectures in this very fishy way for the rest of the lecture, right? So in this very physicsy way. So I want to translate it into mathematics, as I explained before. And then maybe you'll see better what this statement actually means. Now I have to check the time.
O minimal structure is a physical term or a math term?
Oh, this is a pure math. This comes from logic, and it is kind of a special form of geometry. It defines a special form of topology, I should say. Anyway, we get the lecture today. It's a purely mass statement, but it makes this statement, what I mean by finite, much cleaner. Because in all minimal structures, the integer numbers are not definable in all minimal structure because they have infinitely many discrete things. But the real numbers or the real line is definable, but it's kind of connected components, just one real line. So it counts as one, and therefore it's much cleaner by what I mean by finite up there, and it's much stronger. Okay. Very good. So this was just as an aside. So number 2. Now let's go into the geometric string theory setting. I promised you that we have to translate this into string theory in order that we can turn these statements into mathematical statements, right? That we can actually work with them. Now, I cannot give an introduction into string theory, but I can give a few general marks which you might know already, but still it's good to keep this in mind. So string theory is a theory in 10 dimensions or sometimes in 12 dimensions, and then it's known as F theory. So you just believe me on these things now, I hope. Okay. So now what does this mean? That means that if I want to go to 4 dimensions, so 4D, I mean 4 dimensions, then I have to do something with these 10 dimensions. And the usual, or one prominent way of doing this is you split up your 10-dimensional space into a piece which is 4-dimensional. So you imagine that we live here, and then some manifold Y, which has to be 6-dimensional or 8-dimensional, and it has to be compact. So this is actually very important for the whole Swampland program, if you study 4-dimensional theory, that this manifold is compact. Because the compactness of a manifold, of this manifold, relates to the fact that if I have gravity in 10 dimensions, then gravity will be translated into 4 dimensions. And if I want to talk about consistently with gravity or quantum gravity, I have to carry gravity from the higher dimensional theory down to the lower dimensional theory. So compactness is important. And in fact, we see that in mathematics as well, and you see a manifestation of this importance in mathematics as well. So if you want to generate singularities in a manifold, if your manifold is non-compact, you can generate an AN singularity for arbitrary n, right? If you want to generate an AN singularity in a compact Calabi-Yau manifold, people have not succeeded, I don't know if there's a proof, of generating such a singularity in a compact Calabi-Yau manifold with n equals to 1 million. So there seem to be bounds coming from compactness. Yeah, and we will see very clearly, and we also discussed this finiteness conjecture, that finiteness actually comes from compactness. And compactness has to do with gravity. So finiteness has to do with gravity, which fits exactly the idea of the Swampland program, that gravity imposes these additional conditions.
One question. I think there is also this M theory in 11 dimensions.
Right.
Is this?
This is in between, and I suppress it for simplicity. So M theory is in principle nicer than this F theory story. The problem is that 11 is an odd number. And as we will see, at least in most of the lectures here, we want to use complex geometry. So we really like complex manifolds still. And then 4 minus 11 would be an odd number, which is not so nice.
But Thomas, isn't there a nice theory of G2 manifolds? It's in 7 dimensions.
Is this recorded?
There's like a nice boundary. Those things have a boundary. That's a collaborative. Something like this.
Yeah,
Donaldson has period maps for these things. So.
True, but it's I know some of this stuff, but I think it's fair to say that first of all the examples are much more sparse and much more contrived. So if now there are new examples of G2, but they are not as beautiful as kind of just writing down a complex polynomial, and then even the theory of simple invariance or countings and all of these things are not very well developed in real geometry. But maybe we see something in the future because, anyway, yeah, that's something to address in the future. Yeah. So now what is the point? By the way, don't get mixed up. When I talk about Y and compact, this is related to gravity. While funnily, M has to be non-compact. It's not this manifold, but it's kind of the moduli space of this manifold, as we will see in a moment. And this has to be non-compact because of gravity. So please don't mix this up. So this is it can be confusing at times. Okay, and now what's the point? The 4D physics depends on the geometry of Y, so of this manifold. And then my hope is, so the 4D physics are these quantum field theories, are these 4D models. And then the hope is that I can translate these Swampland conjectures into statements about geometry because of this link, right? Because the geometry determines this theory, this effective theory. Quantum field theory. Very good. So now, how does this work in more precise way? And now I have to skip quite a few details, and you have to believe.
So when you say that okay, this has to be compact because of gravity, do you mean that it has to be compact in order to ensure something like the inverse square law at large distances?
Right. Yes. In 4 dimensions.
Yeah.
So in 10 dimensions, it holds these kind of laws. Of course, it's not the same law then, but it holds. But if you want to pull this to 4 dimensions, it has to be.
But this is the thing that you mean, right?
That's what I mean. Yes.
Thomas, like related to this, and this question already was asked, I think, in Irene's talk. So keeping gravity finite is related to the finite volume of Y. So at some point it was asked, so what if you have some manifold with finite volume which is non-compact? So the key thing for all these finiteness statements is compactness or is finite volume?
No,
or how much of that would you?
Well, I would say it's kind of, if your volume has to be finite of your non-compact manifold, the volume has to be very much falling off at the boundaries. So if you want to replace compactness by something, it has to be tameness. Yeah, it has to be sufficiently nice. So we learned this already, and I teach electrodynamics. So your functions have to fall off sufficiently nicely at infinity. But then you have to specify precisely what you mean by this. And what we don't want to do is don't want to put all the information in this fall off. But it's a good point. So you can ask, if you localize your theory on a brain or something like this, can I escape these problems? Well, then you have to tell me how things fall off if you move away from the brain such that I don't. But it's a good point. I don't think anyone has done this.
So I think one could try to also formulate in terms of the spectrum of the Laplacians. We don't want to continue. We want to discrete them. Compact is the easy way to get it.
Right.
If
but
you get other means.
Yeah, very good. Yes, I think that there might be other means of doing this actually, but no one looked into this as far as I know. So now comes another thing which you have to believe me, and this is something which I just do very quickly, we take Y to be a Calabi-Yau manifold. So there are settings where this is very of dimension p. There are settings of complex dimension. There are settings where this is very well understood. But there are other settings where there's arguments if Calabi-Yau is fine, or if there's a lot of back reaction, or it's not Calabi-Yau, and so on. I will just make this assumption. I will do this. I want to get out a mathematical statement. If I can prove it, fine. If I cannot prove it, then maybe it's because I took Calabi-Yau as a condition.
Yes, one question. When you look at m times y, you're really thinking that y has to be a fixed Calabi-Yau, or it can be a family of Calabi-Yaus that are changing. So it will change in the point.
Yeah, yeah. This is the next point, actually. So it will be a Calabi-Yau manifold. What is a Calabi-Yau manifold? It is a Kähler manifold. In particular, it's complex, and it has first Chern class of the tangent bundle equal to 0. And then the Yau's theorem says that then you can find a Ricci flat metric and so on. Yeah, in the same class of the Kähler form. Now, this manifold, and this is precisely what was just asked, is this one fixed manifold, or are these multiple manifolds? No, actually they are families. So they're multiple manifolds. So in fact, we can deform deformations of Y. And these deformations of Y fall into two classes, and in particular, one class will be important, which is the complex structure deformation. Yeah. And then the second class, which I will not discuss, and there is the whole story of mirror symmetry, which comes into play here. Structure. I will talk the complex structure. So you have your manifold, and you can ask, how many complex structures can I put on the space? As a real manifold, you can put a complex structure, but you can also change it a little bit. Still a complex structure. Maybe you can keep the Calabi-Yau condition. Well, it turns out you can change it a little bit, and you can even keep the Calabi-Yau condition. And it was actually proved by Tian and Todorov that the moduli, that the dimension of the space of these deformations which keep the Calabi-Yau condition is given by the following Hodge number. So this is the dimension of this space. I changed the order slightly, and now I understand why I picked this order. Anyway, I will explain this in a moment. There is a certain dimension, a certain fixed number, and one can show that there is a h d minus 1 comma d dimensional unobstructed moduli space of complex structure choices. So as was already asked, I now have to think about this as in the following picture. I have my moduli space M, which parameterizes all possible complex structures which are compatible with the Calabi-Yau condition. And over each point, I have my manifold Y. So over each point Z, I have my manifold YZ, and it can change from point to point, right? And in mathematics, one calls this a family. YZ is a family. And in mathematics, one calls this M the the base of this family. Yeah, and we always say this is the complex. In physics, we often say the complex structure moduli space. Yeah? Just because probably you will hear later some language which easily confuses you, but it's actually not complicated. It's just a different language. It's just the base of this family.
Can Y become singular at some point?
Exactly. So Y can become singular, and that makes this M non-compact. Yeah? So I told you here it has to be non-compact, and in fact, this punctured disk is a very good model. It's a very good local model in one dimension, in one complex dimension of this moduli space.
And so then in the model there from string theory, you have to consider also points in which the manifold is singular.
Exactly. So the manifold becomes singular, but then you can imagine something dramatic could possibly happen. And that's exactly what the distance conjecture tells you. Because the point where it becomes singular are the boundaries, right? Are the ones where are the punctures. The manifold becomes singular, and the conjecture tells us something dramatic has to happen. There have to be the states becoming light exponentially fast. And that's kind of the exciting mathematical statement which comes out of this conjecture. Yeah, it's maybe nice to, well, anyway, I think you memorized this sort of picture. Okay.
So from the, I mean, you have two ways of thinking about this picture, right? So on the one hand, you can compactify on one of these Y set or in another Y set, right? And then you will have to. How do you think these theories are related?
So in principle, if you're in the middle, probably there's a boring relation between the two. The whole point of the conjecture is that as soon as you move to one of these boundaries, the relation is not anymore boring, but there's this kind of exponential power, like this exponential suppression coming in. Yeah, but good question, very good question. Okay, so now there are another few things which I just briefly mentioned is M is quasi-projective. Quasi-projective. Okay. I mentioned already M is non-compact. And so quasi-projective was shown by Vieweg. Sorry, I'm in the Dutch pronunciation. Then there is M can be made smooth. So this is kind of standard, a standard famous theorem by Hironaka. And what do I mean by this? So we already discussed that this is a good local model. I mentioned this at Lips. And I mentioned that it's non-compact, so it has boundaries. Yeah. And what this theorem tells you by Hironaka is that you can de-singularize the boundaries. So if you have imagine that you have a boundary component which is kind of meeting, like 3 lines meeting. This is a picture of the boundary. This would be really a truly singular point. And what this de-singularization theorems tells you is that you can de-singularize this moduli space in such a way that the boundaries, they meet at normal intersection. So they are normally intersecting boundaries.
So for mathematician, you're taking a log resolution of that far.
And why do we need that? We need that in your language, in lecture, because later on we want to walk around these components and we want to associate a monodromy to it. And if I have something like this, I don't know how to walk around this. It's okay. Then it's a non-abelian group. Yes, true, because they don't have to commute. Yeah, but the mathematical theorem tells you can always move to this situation. If you ask me in private, if I understand precisely what is the physics of this resolution in every situation, I wouldn't know the answer. Okay, now it's on record. Okay. Note, we assume that we talk about Calabi-Yau manifolds where the dimension of this cohomology group D, 0 is equal to 1. So there is one holomorphic D, 0 form. And I will call this omega, right? And it varies in the family. So how are we in time? I have to be faster. Now I can be brief on the following discussion because I know that Matt will do this in a lot of detail. And in fact, I already kind of gave a few hints. So I mentioned that we need to discuss states, right? And that was just some abstract words. And I now can make more precise what I mean by there are states in the theory. Okay. And so we need more structure. And there's more structure needed. And this structure comes from the Hodge decomposition. So remember, we have a Kähler manifold, and in every Kähler manifold has a Hodge decomposition. And so I can decompose the case cohomology group into a direct sum of PQ spaces like this. And these spaces have certain properties. And in fact, what you can show, and you will see this in the next lecture, is that this is actually a polarized Hodge structure. And in this polarized Hodge structure, you have a polarization form, which is just, if you look at two elements of HPQ, where P plus Q equal to D, it's just the integral over Y between omega wedge V. And polarized Hodge structure means that there are some sort of positivity conditions which you can impose. But we will see this in the next lecture. So I can be brief. One thing I wanted to mention, because it tends to confuse people, note, we need to restrict to primitive cohomology. So if I take my manifold, which is a Kähler manifold, it has a Kähler form which I call J. And then the primitive cohomology are all the forms in this cohomology which satisfy this condition. And what we will hear later about the variations of Hodge structures and Hodge structures in this geometric setting, it actually should be applied to this primitive cohomology. So to all the forms omega which have J wedge omega equal to 0. In fact, for Calabi-Yau 3-folds and 4-folds, there are nice splits into primitive and non-primitive cohomology. And then mirror symmetry actually acts by exchanging them nicely. So in the last few minutes, Now let me translate these conjectures into mathematical statements. We started a little bit later, right? So I think this is standard problem here that easily runs over time. So now let's talk about the distant conjecture. Conjecture in this sense. Okay. So for the distance conjecture, I take a Calabi-Yau manifold of dimension, complex dimension 3. And what I describe is in a paper by which I wrote together with Aaron Pautel and Irene Valenzuela. I will not write the names. Yeah. Okay. So this was our idea. Our idea was to translate the distance conjecture into this mathematical statement. And the first thing is you have to now compute distances in M. And what is M? Well, M is this moduli space of this, so this deformation space. So now it's something very concrete. We know that it's non-compact. We know all of these features, and we want to compute distances in M. And now comes the little bit, the shock for our Hodge theorists. We compute the distances not in the natural metric on this space, but in the metric which comes out of string theory. And the metric which comes out of string theory is actually the so-called Weil-Petersen metric. So the
natural metric?
Huh?
What do you mean by the natural metric?
So the natural metric is sometimes called the Hodge metric. It's kind of the natural metric induced by this Hodge decomposition. You can think of this. So these are also now coming in a family, right? Because when I change the complex structure, this change. So you get a set here. And then you can define a natural metric on this bundle, and you can pull it back to the manifold, and you get a metric. It's very natural.
Oh, so you basically just replace the signs on the different pieces.
No, actually, you will see in a moment why this is very different, actually. I hope you can spot it. So what is the Weil-Petersen metric? It's also a Kähler metric. So this natural metric, this Hodge metric is also a Kähler metric. But it's not, so it's a Kähler metric. But the Kähler potential, so the potential from what it is computed is only given in terms of this omega, right? This omega was this unique in this case 304. So what does that mean? That means that if I compute the metric, it is essentially a wedge between a 2,1 form, because the first derivative, and a 1,2 form. And this is not the natural metric. Why? The natural metric would also have a piece which is 3,0, 0,3. So the Hodge metric would have both pieces, but this metric, which comes out of string theory, has only this piece. And that makes a huge difference. So in the natural metric, all the boundaries are at infinite distance, while in the string theory metric, some of the boundaries are not at infinite distance. And this is very important. For example, the conifold, which is a typical singularity which you can encounter. So the manifold becomes singular at the boundary, but the conifold is actually at finite distance. And in fact, this fits very nicely what happens at the top. Now I should tell you what are the states. So this was this mysterious words which appeared in the distance conjecture. And in fact, these are special Lagrangian submanifolds.
So your K is the same as the K of the W of the Weil-Petersen method, right?
Oh, sorry. Yeah, absolutely.
And to define this, you don't need to specify a Kähler class. It's only
you don't need to specify a K matrix. Yes. So the special Lagrangian submanifolds in Y. Okay. Now I told you, so these are what I call states. That's a proposal. There could be other states relevant, but these are the ones which we considered, and it seems to work pretty nicely. And so these are special Lagrangian submanifolds, so they are cycles gamma. And now these gammas correspond to integral classes in the third cohomology group. Okay, so this is the one which I'm decomposing here in this decomposition. Well, after complexification, of course. And once I understand that these are the states, then I know how to compute their masses. And the masses is nothing but the volume of these cycles, of these special Lagrangian submanifolds. And then you see everything in the distance conjecture is specified.
The volume with respect to omega, which omega bar?
The
volume with respect to which volume?
With omega. Yeah, I write it down, yes. So the masses, so if they are BPS, if BPS states, so this is just gibberish for mathematicians, of course, but just you can take the final expression. Then the mass is computed e to the k half, where k is this Bipartisan metric. And then our polarization cube, so the intersection product of V is this class, and this form omega. And then this is e to the k Bipartisan half, just an integral over gamma of omega. Of course, that's a complex number, right? Because this is a 3-0 form, so the complex number comes out. So what do I mean by mass? Then the mass is actually, oh, it's unfortunate, that's down here. The mass is actually the absolute value of the set. So the mass of V is actually the absolute value of the set. So just volumes of cycles. So now what does the distance conjecture state? It states that, and I will end on this. What does the distance conjecture state? It states that these volumes of cycles, if I go to the boundary of the moduli space, they have to behave in a certain exponential way. That's what the conjecture says. And it also says that it's not just a single state which becomes exponentially light, but there is a whole infinite set of states which becomes light, right? So in other words, I now have the following math problem, and I will end on this. Sorry for running over time. We have to classify the boundaries of M, of this moduli space, and we have to understand the asymptotic form of the Bipartisan metric, because we want to have infinite distances, and of this function z, which depends on my integral class. Yeah. And by the way, this function z is also what is known as a period integral. So we have to understand the asymptotics of periods, period integrals.
So one question. So the Holmberg volume from omega, we may not be able to globally choose it across all Calabi-Yau manifolds.
We
right?
are not able to do that.
Because they can be monodromy.
Exactly.
So how do you make sense of this thing? If you can't make a global choice, then how do you get a well-defined mass function out of this?
Yeah. So once you once you fix a charge V, then you have then you fix a frame, so to say. Of course, when you make a monodromy transformation, you could change V. But if you fix a V, then this is not anymore dependent on the monodromy. If you do a monodromy transformation, you can shift it to changing this class V. But you're absolutely right. So we have to try to look at local behavior of periods near the boundary. Okay, so this is exactly what will be discussed in the other lectures to some extent, and I will also try to fill in aspects of this asymptotics of periods or the period map. I don't know if Ben will actually talk about the period map, but for us periods, it's nicer to understand it's just these integrals. Mathematicians like to understand period maps, which is somewhat cleaner. Number two, one has to find a lattice of charges. With charges, I mean integral classes V with M of V going asymptotically as e to the minus lambda distance in the Bipartisan metric. Okay. So of course this mass depends on the point in M, right? Oh. Yeah, this is physics. Right? So in physics, we tend to agree to name everything with the same letter because it all means something. So M is the mass, and so it's called M. The moduli space is also called M, but it's a curly M. Please, it should be not confusing you. Okay. Very good.
Sorry, lattice of charges is supposed to mean the same thing as tower of state.
Yes, exactly. Lattice of charges, now it's a clean statement. No? I want to have a lattice of charges which has this behavior. And finally, and this is of course one of the trickiest part, you have to establish the existence of the BPS state.
The lattice of charges is the same as the third homology.
Yes. Right.
Yeah, but maybe it's smaller, right? You don't need to have. It will be some
subset.
Some subset.
No. Yeah, exactly. Not the full. We will see in one of the next lectures. We will see that some of the charges, some of the lattice points, they will get heavy. So the mass grows exponentially towards the boundary. Some of them will fall off exponentially. And depending on the boundary, there are more states which do the one and more states which do other things. So it's very intriguing. So, and then establish the existence of the BPS state. Oh, Jesus. So therefore we have to find the actual cycles that shrink. And this really goes into the connection between Hodge theory and the realization of shrinking cycles in the manifolds. And that's what also will be talked about, I think, by Matt, right? To some extent. To some extent in his lecture. So this is one of the conjectures formulated as a mathematical problem, and now we can use this powerful machinery to attack. And what I will do in the third lecture, I just have half a page actually, one page on the finiteness conjecture. I will postpone this to the third lecture, no problem. I do the same thing for the finiteness conjecture. I take this gibberish finiteness conjecture and translate it into a mathematical statement, and then I will prove this mathematical statement. Thanks.
Thank you.
Sorry for that.
We're super late. If you like coffee, we should spend approximately 1 minute with this. I don't know if there is any question coming from the online participants. No. Any urgent question from here, or you can postpone it to the coffee break? That's actually better, so we can.
Yeah, I will do better next time.
No,
Sorry
that's
about
fine, that's
that.
fine, that's fine. Thank you so much.